It's my pleasure to introduce Professor Devi Prasad Dogra, who is currently working as an associate professor and head of the Department of Computer Science and Engineering at IIT Bhubaneswar. Professor Dogra received his PhD from IIT Kharagpur and Tech from IIT Kanpur in the year 2012 and 2003 respectively. He worked with ETRI South Korea as a researcher from 2006 to 7 and a research group leader in Samsung Research Institute, Noida, before joining IIT Bhubaneswar in 2013. So with 130 plus research papers in international journals and conferences, and patents in areas including applications of AI, ML in visual surveillance, intelligent transport systems, computer vision, augmented reality, and healthcare analysis. He's a senior member of IEEE and currently a treasurer of IEEE Bhubaneswar section. He's also an editor of SNCS and JMIS journal. He is an independent director of IIT Bhubaneswar Research and Entrepreneurship Park, a Section 8 company of IIT Bhubaneswar. His research interests majorly include artificial intelligence and applications, computer vision, visual surveillance, intelligent transport systems, augmented reality, and applications. With this short introduction, now I would like to request Professor Devi Prasad Dogra sir to kindly start the session. Over to you, sir.
Good afternoon, Dr. Deepak Naik, and good afternoon to all the participants. Thank you all for inviting me to this. I am privileged to, deliver a talk on applications, visual surveillance and its applications. And I believe this talk will be of some interest to the participants, and it will be interactive in nature. So let me share my screen. So please let me know if my screen is visible to you or not.
Yes, sir. It is visible.
Yeah. Okay. So, so my audio is clear?
Yes, sir. The screen is visible, audio is clear, sir.
Okay. Thank you. Good afternoon, participants again. So when Dr. Naik approached me, I thought that I shall be speaking something about visual surveillance and particularly its application, and I'll explain some of the research work that we are carrying out at IIT Bhubaneswar. Obviously, this research work have been carried out by my research team members, my PhD scholars, my master's students, postdoc students who have worked, and with some international collaborations with KIST team. And this is part of the research outcomes that we got it during last maybe 5 years or so. We have a lab which we call it Visual Surveillance and Image Understanding Lab. So you can look into the lab also website to understand things. Now, our primary objective is to use application, AI and machine learning, particularly for dealing with anomalies. Okay. So anomalies, when I'm talking about anomalies, I'm talking about vision-based anomalies. So the vision-based anomalies are extremely important these days because millions of CCTV cameras are getting installed across different countries, different cities, and they are capturing data. So how good we are in dealing or processing such huge amount of data, that is what visual surveillance and vision-based models try to do it. Now, what is anomaly then? So we call an anomaly something, an action that actually deviates from regular behavior. Okay. So regular behavior, it can be an unexpected one, or it can be sensitive with respect to certain environmental conditions. Okay. And let's say, for example, in visual surveillance, you have numerous abnormal events or behaviors possible, including, like people are walking, suddenly falling while walking, fighting, kidnap, explosion, vandalism. These are only a few examples, but you can have many such, scenarios where visual anomalies are happening. And also such anomalies are possible depending on many factors, including the camera settings, the camera placements, recording perspectives, interactions with the real world objects. These are primarily the settings that, and based on these settings, actually some of these anomalies can be categorized. For example, if you see two people are interacting from one angle, it is possible that from other angle it looks like that as if they are far away. So it depends on how the camera perspective captures those two persons, right? So it is quite sensitive to the camera settings and placements, recording perspectives, and so many other environmental factors. Now, let us see some examples what kind of anomalies we often see, particularly in Indian context. If you look into it, I'm showing you three examples on the top row where you see the first one is a rally. It may be a political rally or religious rally, whatever may be, but you can see that a large number of people are gathered within a small area, which may lead to some unwanted situation like a stampede-like situation. So that's why this is important to keep an eye on such scenarios. Similarly, when people are moving in a more regular pattern like a marathon, also you need to observe it whether people are maintaining proper posture, maintaining proper distancing, or whatever may be the other as per the condition. This is also required. And for example, religious festivals like Puri, I mean to say that I'm from Odisha. We know that how this festival is popular, and during the month of July, June, July, when this happens, how many people actually are accumulated or gathered in the city of Puri, holy city of Puri, on the day of Rath Yatra and subsequent days. And it becomes a very challenging scenario for the administration to maintain this large amount of crowd, avoiding all kinds of scenarios like stampede, and there are many other serious possibilities, right? Now, if our inputs are like this, we have CCTV cameras which are capturing large gatherings. How do you deal with it? So in manual monitoring, what happens? You deploy somebody, the person actually looks into it, and it requires precise human effort to identify something wrong. And this process is error prone because human being will be subjected to certain kind of fatigue, certain kind of biological needs, right? All these things are there, and also it is time consuming. Whereas if you basically apply a computer vision based monitoring where it requires less human efforts, it can do better information fusion. You can capture information through multiple sensors like cameras, audio sensors, some other sensors wherever possible, and then you can fuse them. So you can always do better information fusion, and it can process high volume of data at less time, because if you need to process more data, you can simply increase the hardware of processing so that it can actually process more amount of data. And it has also been observed over the time that it is prompt, accurate, and intelligent. Whether how accurate it with respect to human monitoring, that there can be questions, but still research has advanced during last 3-4 years that it is now pretty comparable with respect to the human interventions. Now, let's say dense crowd, how do we model? Okay. So sometimes back we started to understand that, and not only us, many people have started to understand that whether we can apply some physics-based models for crowd dynamic analysis. So in terms of randomness and energy computed with the help of, let's say, Gibbs entropy, kinetic energy, all these things, it's possible. So a typical pipeline can look like you have the video, you calculate the optical flow, you do the quantization, then do the connected component analysis, energy and entropy calculation, and you do the analysis, right? And examples like when you apply these things, how do you calculate the energy? Energy can be simply calculated by moving pixels, and you just apply half mv square, assuming that motion is represented using velocity, and then in a mass you can assume unit mass. So basically, that's not that difficult to do it. Okay, so energy calculation, and then you basically do it for the entire frame. Over the frame, you take an average, or you apply certain other statistics also. Okay, and you get some quantification of the energy of the whole frame, right? And again, entropy for the whole frame, you can calculate it using. Here I'm giving an example of a entropy that is Gibbs entropy, but you can actually try with some other methods also. So considering each connected component as a microscopic state and the frame as a macroscopic state, the entropy can be estimated using this formula where we represent the number of groups in a frame, right? So if there are multiple groups which are close to each other, you calculate the entropy of each and every group, then basically take the average. So when we do a simplistic physics-based observations or physics-based calculation or modeling, there are certain observations. So our observations tell us that if significant fluctuations are observed in interframe energy, interframe means when the energy, you are calculating energy on per frame. So when you calculate the interframe energy, it can be attributed to fast moving if the fluctuations are high, right? And if the fluctuations in interframe energy difference are low, then the crowd can be assumed to be moving at a uniform but lesser velocity. Similarly, more fluctuations in the entropy curve indicate varying randomness in the crowd. And we have also observed that for constant entropy, the randomness can be assumed to be less in a particular video. So now with that, when we actually taken a step forward, we wanted to segment that. If a crowd is flowing, say for example, let me go back to the slide again here. Let's say this is the crowd which is flowing. Okay. Now I want to understand that whether this crowd is a violent crowd, or this crowd can lead to some untoward incident later stage or not. So for that we need to basically apply a higher level of processing. Now let's try to represent this crowd first. Okay. So for this, what we did, we actually applied a conventional approach, which is called based on Langevin model. So we assume that, let's assume that this is a particle. So each and every particle is basically a P is representing, let's say, Brownian particle. We are assuming they are not one P doesn't mean that one person is basically a group of optical flows that is representing a person, right? And then in a typical Brownian, if this is a Brownian particle, which is, we assume that crowd also behaves like a Brownian particle, which may not be exactly correct always, but with certain relaxations you can do it. So what kind of forces actually in a typical Langevin model particle experiences? These forces are mainly, it has three components. So one is obviously the random fluctuating force, which is green, which is more or less like noise. Then you have Newtonian force, because obviously it's attraction force. And then the frictional force, because there is a movement of the particle, so it experiences certain frictional force, which is denoted in blue line, right? So when you combine these forces, and Langevin equation actually does this one, and then it tries to basically find out the equilibrium state. And after that, you actually, so basically this is the equation, we get it. So internal is basically the external drift and confinement and disturbance. Disturbance is nothing but the random force. Drift and confinement is within the, it's basically the Newtonian force, and external basically people have some goal, so they are moving towards certain direction, so that comes from the external force. So you can see that the external force is this one, in blue line, internal force is this one, Newtonian force, and then the random force is basically the disturbance. And how do you do it over a group of people or group of pixels or moving pixels, whatever you call it? Let's say you group them based on some similarity. Like you can see that these three groups, like G1, G2, and G3, these particles. This is just for demonstration only. We are showing it that if these particles are grouped in a particular region, assuming that they have certain similarity. That's the meaning of grouping. So with the similarity, when these particles actually move, then what kind of forces they experience? So that is basically modeled here itself. And then when we applied this model, and if we see that this is the model, proposed Langevin model, which we can apply it. And but to start with, you need initial processing. This initial processing, nothing but you basically calculate the optical flow, like dense optical flow. Then you do the quantization, then you do grouping and particle grouping, and then you become the key points. You extract the key points. Basically, you get these key points and grouping and key points. After that, actually, you do the model. So for initial few frames, you do the prediction based on the difference, but subsequently you do the prediction based on the Langevin model, which makes it faster. Now, from second frame or third frame onwards, if you see that t greater than 2, you avoid this computationally intensive optical flow path. So you only follow this path, prediction path. But again, you reallocate it after, because the noise gets added because of the equation has a noise disturbance. It has a noise. Obviously, you can understand that this prediction will not be accurate for a long time. So it will come back with certain error. So when the error reaches beyond a point, then you again do the optical flow calculation. You re-estimate the grouping and again apply the Langevin model. So this is how actually it runs, and then you can segment the flow. And with all these, once you estimate the velocity, then you know the velocity, you know the previous location, so you can always calculate the new location. That's why standard, by doing the integration, you can calculate. If you know the old velocity, with the help of the model, you can always calculate the new velocity. And you know the velocity, then you do the integration and you can actually calculate the position. So you know x nu and y nu, then you know the position of the group. So that is what we did it. And then how do we basically calculate the drift and confinement? These are standard, drift and confinement, which is basically depending on the mass, because drift is basic confinement. It talks about the, within a particular region, how it is confined. So that means this is going towards the towards certain region. So that gives you the confinement, and drift basically gives you with respect to the mass of the particle. So how much it is basically deviating, right? So all these you can estimate it from a given statistics, and you can fit the model. Now, when we fit the model, we can calculate the segments. Like for example, if you see, I'm showing you some samples where, let's say, top row is a set of frames where people are moving, where the ground truth says that red and green regions are nothing but the flow. So some people are moving in this direction, some people are moving in this direction. So when we try to do it using Langevin model, you can see that we are getting bicolor separation, so which is not bad. Okay, so this is what we actually achieve with respect to the existing model. The fourth row, if you see, this is a model proposed by Ali et al. Okay, where it was not able to segment the group properly as compared to the ground truth. This is one example. Similarly, when you test it on, let's say, another data set, for example, Puri Rath Yatra, you see that the crowd mainly traveled from this to this because Rath was getting pulled. So basically the movement was around this direction, along this direction, along this direction. Okay, these are subsequent frames. So you can see that the proposed model was able to segment this flow quite accurately, whereas in the other models, you can see that there are a lot of noises coming. So these are, some results which I'm showing. Now, this is dense, crowd I was talking about. Now, what about the scenarios where we don't have, much crowd, but these are more, serious in nature in terms of anomalies. Okay, so I will show you some videos which may be slightly disturbing because these videos are public videos and of accidents and certain types of disturbing facts. So please bear with me. So let's say, let me actually play this video. If you see, I hope that the video is playing. If you see, this guy is hit by a vehicle. Okay, this is a real life scenario. So this is an accident one. So woman abuse, a person is actually abusing an woman. So these are all available through, these are standard data sets. We have actually created our data set. These data sets, like for example, this one is from rare anom data set, the top right one. The left one is from CADP data set. Now this is a case where basically, burglary or, somebody is trying to break the gate. On the left, you see that person will try to come and try to basically force, breaking the gate. So this is from UCF prime data set, which is a standard data set trying to break the gate. Now the difficulty here is that whether this person is trying to break the gate, whether he's the owner or not, that we do not know. It is also possible that the owner is also opening. So that's why the challenge is there. Again, this is another one, road accidents, which is taken from the XD violence data set. So what I mean that these are all scenarios where we need, immediate attention, and we want to understand that how these cases can be detected quickly and how we can basically create models, right? So then comes the detection of anomaly. So for visual surveillance, security agencies often install thousands of surveillance cameras that we have already discussed. Okay, so it is really not possible to monitor the huge amount of long duration video data manually. Okay, and manual processing is actually time consuming, time intensive, error prone. Okay, so hence there is a need to go for automatic detection and recognition of abnormal events. Okay, so there are three primary challenges while we do it. What are the three primary challenges? I call them that three key points. So if you look into these key points, the first key point is the rear. If you see, when the CCTV camera is capturing the videos on, let's say, long-term basis, it is capturing, it's a 24/7. Now in 24/7, it is capturing, you would like to identify only that portion where the anomaly is there, right? So that's why it is rare, and the anomalies are not common. You don't find road accidents on everyday basis on a particular location. So it's very rare in nature. So that's why it is rare. And often these anomalies are short duration. So short duration means they don't happen for a longer duration. They will happen maybe for a couple of seconds, 2 seconds, 3 seconds, 5 seconds. So you don't have much data available for that also. And the third one is in disguise in long hours data. So you'll have to find it out in a long hour recording where exactly. So these are a few challenges which we face, any computer vision community face while they do it. Now, if you detect such anomalies, what you would like to do it? Let me tell you some examples where, some people try to detect it. Say, for example, I'm showing you two methods. Let's say there was one accident which happened. So these are the frames. say this is frame number 10, this is, I'm just giving an example. This is frame number 10, maybe this is frame number 20, this is frame number 30, something like that. Assume that they are actually in temporal domain. Now, with respect to that, if you see this shaded region, it tells that actually when the event happened. Okay, so the event happened between frame number, let's say 270 to 450, this event. Okay, this is the ground truth, right? But you can see that there are small peaks here, which is also a false positive. A small peak means it is not anomaly. This is the anomaly score. If I assume that y-axis is anomaly score, the methods are also saying that, see, there is a slight, slightly high value, which is 0.2, above 0.2, which may not be exactly an anomaly, but there is something to be suspicious. But if you look into the scene, it seems to be there is nothing. Whereas when you come to the original anomaly case, you see that the value of anomaly score is quite high, right? And these two are methods actually. This orange is one method and blue is one method. So these two methods compare. When we say that, what is the meaning of these two methods? These two methods say that actually the blue method predicts it on time, whereas the orange method takes some time to predict, right? So this is what we wanted to tell you, that you see one method is actually doing the prediction very on timely manner, another method is actually taking some time to do the prediction, right? So that is what it tells. Similarly, for one more event on the right side, if you look into it, okay, like the orange method actually assumes that initial part is also an anomaly, whereas the actual anomaly is happening when the blast is happening, right? So this is where the methods actually differ. So these two methods which are pointed out here, blue is the fuzzy fuse method with cell flow, and Sultani et al is C3D based method, right? So now let's see that how basically, if you see on the left side, carefully observe the left side, there will be a bomb blast. Okay, and accordingly, after the bomb blast, you will find that the the anomaly score goes high, pretty high. So you carefully observe that when it is actually happening, when the bomb blast is happening, then exactly during that time the score is becoming extremely high, right? Similarly, here, if you see somebody is trying to put a car on fire, so this is the entire event. This event takes time. That's why the anomaly score is pretty high for a long time, because the anomaly score remains high, because this act itself, pouring gasoline or petrol on a car, it takes some time. So that's why it takes time. So these are two different visualization cases which I would like to show. Now what happens? Now all these methods are trained using annotated data, right? But what happens if we do not have the annotation available, or if you don't have the annotated data, right? So this is where the problem actually starts. So we can then think about designing, anomaly detection algorithms which in an unsupervised way. So unsupervised way, how do you do it? So one way can be, can the dynamicity play a role? Dynamicity means how dynamic the scene is. So let me show you some pictorial depiction. If you look into it on the right side, there are two videos on the left side and right side. So let me first play this one. You see that this is nothing but a simple physics experiment where basically the one side there is a hinge, and this rod is basically getting some vibration, right? Now observe on the right side what is happening. So there is a marker which actually says that what is the displacement happening. So this displacement. So if you look into it, the displacement actually varies. Like sometimes it is high, sometimes it is small. Obviously, this is just by the nature of laws of physics, and we know that the displacement will be very small. Displacement is very small. So when you go you see that the displacement is pretty low. So as you go, you see that as we move, the displacement is becoming smaller. It is becoming smaller. It is becoming even smaller. It is becoming even smaller, even smaller. You go beyond that, you see that it is becoming stationary. So now you will see that it is becoming even smaller. So what does it mean? This experiment tells that the dynamicity in the nature or dynamicity in the event can actually, so this is just displacement. Displacement, I have taken it as a measure of dynamicity, but this can be, this can be, done in a different way also. But this is one measure. Displacement is one measure, and that can be used as a metric for measuring the dynamicity, right? So then, yeah. Similarly, let's say another example. Let's say this part is a scene where there is no earthquake. Let me show you. So if you look into this video when there is no earthquake, when the same scene with an earthquake happens, so what is happening? If we can see that the entire scene is basically moving. So okay, so this is called basically the dynamicity, and this dynamicity, if we can use it, exploit it properly, then probably we can identify that whether this is an anomaly event as compared to this one. So how this can be? There is a paper in WCB 2024 which actually exploited the dynamicity, and the authors proposed a model with a typical RGB and I3D based RGB stream and I3D based flow stream. So if you see what they have done, this is a video segment. You also calculate the optical flow, and from the optical flow you estimate the dynamicity. Now, in the pass one, you estimate the dynamicity, and then you basically change this dynamicity score with a cross correlation. Okay, and you generate the level, pseudo level. Pseudo level means whether it is anomalous or not based on that, and essentially you train the model. And this one worked good, but even better models actually came, toward the last 1 year also. So how this method performs? Let us see that. If you see, there are two they have actually pointed out two different metrics. One is called anomaly score. Anomaly score, if it is higher, that means it is more anomalous. Another one is dynamicity score. So, and the blue one is dynamicity score. And this shaded region actually tells that where the actual anomaly happens. Now, if you look into the correlation of these curves, you will find that blue and red are actually correlated. They are not exactly same, but there is a correlation. So that is what the authors actually established, that there is a direct link of dynamicity with the anomaly score. And this is also, a similar pattern can be seen in the another example also, which is shown on the below. So that is what actually they have experimentally proven. And if you look into it, the explosion video that we have looked into, there are certain cases where you see the dynamicity plays even better results. If you see the explosion here, okay, so this is still explosion and a post explosion going on. Exactly, explosion happened here, but after explosion also a lot of things are there, right? So that's why the scene was dynamic. Maybe the objects thrown away. There were a lot of change in the scene. So that's why dynamicity score still remains high. However, the anomaly score remains low. So this is probably dynamicity plays much better role in as compared to typical anomaly. And similarly, this is conversely, you see that here actually this is not an anomaly. Okay, dynamicity is saying that it is not an anomaly, but anomaly score is saying high, so which is also contradictory. So that's the reason always anomaly scores which are generated using other methods, they may not be always trustworthy, right? So far we have not actually discussed about the objects which are involved in the anomalies. So from now, I will try to change my focus on showing some anomalies or visual anomalies in visual surveillance where object interaction is important. When the objects are interacting with each other, how things actually become. That is what I'll show you. So let's take a simple example. So this is a road scenario, publicly taken data set. And you would like to identify that where there is something wrong in the scene. If you look into it carefully, this is the portion where actually the anomaly is there. A car was hit by something else, something like that. And this is only one frame. The video, you can, if you play the video, you will see that the car was hitting another car. So what this, one approach can be, you basically identify the K-body interaction. K-body interaction means like each and every frame you focus on K objects and within the frame. So K can be 2, 3, 4, 5. Okay. So these are all different body interactions, and then based on that body interactions, we extract features, right? And this method was proposed in 2022. It's a slightly old one, but you can see that what it does after the K-body interaction, it actually creates the positive back, the interactions which are positive toward an accident and interactions which are negative toward accident, okay, or anomaly. So you basically do this, positive back and negative back, and then do a, kind of refinement algorithm. And with the help of a conventional mobile net based classifier, okay, it was able to actually detect the location where, or the hotspots where the accidents are happening. And then once you have done the frame level localization, you can do the labeling of the events, and the labeling of the event can actually give you the descriptions. This is basically pre-chat GPT, descriptions. If you ask these days, give a video, the video will be completely described by the, today's VLMs. Whatever I'm showing you, 3-4 years back. So earlier, the researchers actually used methods like detecting objects, then identifying the type of the object, and then their interaction. Then they generate an text like this. Like description is a like start of the accident. It says that frame number 10. Number of objects. It says that 3 objects. Type of objects, it says that 2 cars, 1 motorcycle, and area of accident is 28%. These are all more like an object detection based things. Things have changed during last 2-3 years, where you do not need to do specifically these things. Your LLM models will tell you. So localization, actually it helps. So for example, this is somewhere the accident happened. You want to do a localization like this. Also, you would like to do an impact analysis, so that this also gives you some idea that how much damage happened to the scene, or how much rescue effort is needed to repair the scene, or to send the medical staff. Okay, so this one was tested on some video data sets, and I can show you that how basically it generates the report. So you see the accident, and it generates the textual description, right? So this is on one scene. Okay, another scene on a different condition. If you see that the vehicles will move, vehicles will collide, you see that vehicles collided, and automatically the report came as an accident. Then even in the night scenario, if you see 2 cars actually collided, and then the report came, right, with area of accident. Area of accident is obviously the portion. You see that this is where another accident is shown. So these are a few samples which I'm showing it to you. You can actually see those papers. The authors have provided many such examples, right? So, and then comes some real world, the challenge that often computer vision community face is that how to train these models. You need a lot of data. You may not be able to get every scenario and to be covered. And unless you have enough or sufficient amount of data, you cannot train your deep learning models. So what to do then? That's why people actually started thinking about generating synthetic data. Okay. And real world data set. This real world data set, this is actually our data set. We have recently published it. Recently means 2 years back in pattern recognition. This data set actually contains, 17 categories. I think 1, 2, 3, 4, 5, 6, 12, 17 anomaly categories and 1 normal category. So 17 anomaly categories, they include, you see that abandoned bag, ambulance movement. We call it rare anomaly because these anomalies are rarely occurring. Animal abuse, animal attack, building collapse, crowd violence, earthquake, drowning, lightning, machine failure, kidnapping, industry failure, person fall, train accidents, wheelchair movement, sports failure, women abuse. Okay, these are categories. Some of them are really rare in nature, and the last one is normal. So we actually created a large data set for this one. You can see the statistics of the data set. This data set is publicly available, which has, I believe, more than 1,200 videos or more than 1,000 videos across multiple classes, right? And against each and every class, we have actually created negative samples also. Negative samples means we ensured that there are sufficient number of negative samples so that your classifier is able to distinguish it. During training, it should be able to distinguish with similarly looking events like. And you can see the spider chart of this one, which shows that the distribution of different number of videos. These videos were actually collected from the internet and annotated properly, and then they have been tested. So like I'll show you some examples. This is animal attacks. Animals are attacking the caretaker or caregiver. You can see that these are the events which we would like to, like somebody, you see that somebody is drowning, somebody is falling down in the swimming pool on the right side, right? Similarly, on the bottom right, you can see that one crane is falling because of the heavy weight on the tree. So the crane is falling, right? Similarly, you see that there is a building or a kind of structure which is getting collapsed due to certain precision destroying technique, right? So these are a few samples which you can see, and there and some more samples you can see. You see the interesting case is on the bottom right. So it's a child lifting case. Now the point is that whether the parents are coming and picking up the child or somebody is actually picking up the child, lifting, this is what is an AI model should decide. Now this is an earthquake case on the top right. If you see, here is an industry factory failure. Here is a lightning. So some lightning happens. You see that this is what happens actually, and you would like to identify those scenarios in using AI algorithms so that you can develop models which can detect these events, right? Now, when these models are tested on benchmark or these data sets are tested on benchmarks, you will find that sometimes it does good, sometimes it does bad job. For example, building collapse. Building collapse, you get pretty good accuracy or ratings like 0.7 is the confidence, which is quite good, whereas earthquake is also good, whereas kidnapping is also pretty good, 0.91. Whereas in some cases, machine failure, animal attacks, and machine failures, you see that they are not always, confident. For example, whether it is animal attack or animal abuse, these two things are quite confusing, right? Another one is machine failure or train accident, railway accidents. They are similar looking events. So that's the reason we don't get. So now this is all about the data set that we have created, and we have published this data set. You can actually use this data set for your own research also. But what about if we don't get enough data? That's why this comes, that synthetic one. So one of my students, he actually worked on it, where he created the data set using synthetically generated videos. Now, synthetically generated videos have been generated using games, computer games, like GTA 5 game was used to create road accidents, and then based on some architectural novelty, we actually proposed a weight sharing mechanism. Because if an event is shown from 5 different angles, you see that on the left side, actually the same accident is seen from 5 different angles. I'll show you some more examples in the next slide. You will see when an accident happens, if you look into from different perspective, how it looks like. The features are different. From some angle, you may be able to identify it as 2 vehicles are hitting. Some other angle, you may not be able to do it. So that's why we want, because in real life scenario, you do not know that where your cameras will be placed. Your cameras will be placed at different locations depending on the scenario. You don't have any control over it, right? So if you do not have any control, then how do basically deal with it, right? So that is what this paper actually proposes, where I'm showing you an example with 5 cameras or 5 different views, and then similarity of these views, like when you create a confusion matrix, which angle is actually similar to what angle. So it can be represented using a typical graphical structure, and then accordingly the spatiotemporal feature selection can be created, because based on this one only you can create the spatiotemporal feature extraction. Now let me show you that how these angles. Let's say this is one video where I mean to say that one scene of accident where 5 different angles, from 5 different angles the scene is captured. Okay, I'll show you the actual video. This is just an image representation, I believe. Yeah, now see, the same accident is seen from 5 different angles, right? So if you see it from 5 different angles, so your visual features will be different, right? And on the right side, I'm showing you the confusion matrix. That means which angle is actually matching with which other angle, right? So this gave us, some idea that if in real life scenario, cameras are varying, placed at different angles, then how the model should adapt to that. That is what basically we wanted to test it. Similarly, if you see another example where you see this is where the accident happened. Now slightly different angle comes from here. If you capture it, you see this is what. Now if you see it from another angle, this is slightly different angle. Okay. Now if you see this is from another angle. Okay. If the accident happens, how it looks like. Now if you see another angle, if you see it from a completely different angle, how it looks like. So this gave us much knowledge about that when an accident happens, if you see it from different angles, then how it actually looks like. The good thing about such experiment is that in real life, you do not know that in which angle, from which angle you are actually capturing the video, because that's not in your control. You are only, fixing the CCTV camera. Where the accident will happen, that you do not know, right? So if that is the case, then your model should be intelligent enough, irrespective of the angle of the camera, so that you can detect it as an accident. So that's what it basically it did, right? And when we actually tested this one, we have found that when we tested on real videos, we have trained on synthetic video, and when we are tested on real video, we were able to detect the accident. You see that in the testing, we have only used this sort of videos. Okay, and in the training, sorry, in the training, in the testing, we have tested with synthetic video as well as real video. If you look into the accuracy, it is pretty accurate in detecting accidents in synthetic as well as in real life. This is what is the takeaway from this research, that even if you do not have real life data, if you are able to generate synthetic data through some means, through gaming platform, through any other simulation platform, depending on what kind of scenarios you would look like, then probably you will be able to create models that will work on real scenarios. Now, if you see here, this is on tested on synthetic. When full weights are shared, all weights are shared with each other, we are able to detect, you see that accident. These are the high spikes are when the accident is actually happening. Okay. Now, from now for the next 10-15 minutes, what I'll be talking about you, what happens when the models are becoming much stronger with respect to the textual descriptions. So that's why since 2023 onwards, when the LLMs came, then people have started thinking about why not to use basically a typical VLM and LLM based approach to see that whether surveillance can actually gain from this one. So the next part of the work, what I'm going to show you, it actually involves LLM also, right? So let me show you what it was going on. Okay, so this is basically one work which we have been carrying out for last couple of years on pedestrian attribute recognition, because often these anomalies involve human. So if you would like to, categorize or classify the pedestrian attributes, pedestrian based on their attributes, and re-identify the pedestrians, then we would like to use their attributes. Attributes include their clothing, their views from front, back, accessories they are carrying, mobile phones, etc. Whatever maybe, they may be the dress and other things. And various researchers have attempted person re-identification, person retrieval, and scene understanding using pedestrian attribute recognition. So pedestrian attribute recognition is actually part of many research, right? So how the PR has advanced, I'll show you typical research work that we have carried out at our institute, where we have got some success, including a few good research papers, where we initially defined what is PR, then why it is so important, what's the problem and what can be the solution. Then we found that the biggest problem is the data set, right? So pedestrian attribute recognition, particularly for a country like us, is not available. So we actually proposed a data set which is not for only our country. We actually tried to include people from data sets involving people from multiple countries. At this, I recall it was probably 11 or 12 countries across multiple continents. And then we also proposed a clip-based approach, which actually got. Now, how it works, if you see that in pedestrian attribute recognition, usually the existing research, what they say, that they actually describe things like a person like this one. You have two persons like this one and this one. They are saying that short hair, paper bag, black trousers, white shoes. These are explicitly mentioned that this person is having this sort of feature. Similarly, this person having this sort of features. So another data set, they actually give more detailed one, right? So when we compared the existing data sets, we found that there are certain limitations of these data sets, including their number of attributes, the outdoor, indoor presence, the total number of frames available, total number of images available, all these things. So we found that there are certain limitations. First of all, some of the attributes in these existing data sets, they are dominating. So that means that there will be a bias in the data set. Some classes are too large, some classes are small, some classes are moderate, all this. So distribution is not even. And in few cases, the instances consist of two pedestrians actually in a single image, leaving the annotator in confused state. So when you give an image to an annotator to annotate it, there should not be any ambiguity. Because of multiple persons are present in an image, so ambiguity comes there itself. So this is, I'm talking about the existing data sets. And we do not have sufficient counts to include into the data set, and there were redundant entries. There was not observable. Some features you may not be able to see it from the, say for example, if a person is wearing a sunglass or not, if you look it from the backside, you will not be able to see it. So not observable is an important feature. So after all these things, when we designed a data set, we actually, we took care about all the limitations, and then we actually proposed a data set with a very short size, small size data set, like a 30,000 only samples, which is pretty low as compared to the other data sets. If you look into it, these data sets, some of these data sets contain 1 lakh images, 84,000 images, but our target was something different. We wanted to do it on a reasonable size, but our focus was more on the attributes. So what we did, we actually created 30,000 pedestrian samples, collecting data from internet, and then 25 wide attribute categories and 140, because out of this 25 there are subcategories. So total 147 attribute options were there. So resulting in almost 7.5 lakhs of fine-grained annotations. They spanned over 12 countries. Yeah, I was right. This one, all the pedestrians were from 12 countries, 4 distinct weather conditions, 8 different public places. That's why it actually gave us the diversity in the data set. So that this data set, large diversity. Now you can see that the attribute list. These are only the upper level list. Lower level lists will be, there will be many other subcategories under each and every category, right? So you can see that this is a huge set of attributes, right? And see that. So when 25 attributes, each and every attribute, like accessories can be bag, trolley, umbrella, nothing, bicycle, bike, others, and not observable. Height can be short, medium, tall, not observable. Weather can be sunny, night, rainy, snow. So basically, we tried to include all possible scenarios so that it doesn't miss those scenarios. And then, so how the annotation was done? Annotation was done using a tool. So this tool, we have developed it, and then we have asked our volunteer. It took us a long time to create the data set now, which is publicly available, and people are actually using it for their research purpose, which is publicly available, and they use it, right? And then there was a baseline approach also, which we actually published in WCB 2025, which uses a typical, VLM model where the description of the image is given as well as the image is given. Then you have a clip-based encoder, visual encoder, audio and textual encoder, and then basically you do the things which is basically done in this architecture. I'm not going into the details of this architecture. You can actually look into our paper, which with all the mathematical details and things are there itself. And when we actually generated prompts for each and every pedestrian. For example, if you see, the full prompt looks like a photo of a person with a gender, male, age, adult, hair, short, this one. Whereas the random prompt was like this. when we gave some context, the prompt was improved. A photo of a person with a gender is female, especially a face mask is present, hair long. So this gives much more, better prompt, right? And when it was tested, we found that the clip-based model is actually performing in terms of, mean accuracy, as well as precision recall. You can see that all values were pretty high when the BIT-based backbone was used, right? So, and they were tested on multiple data sets. For example, they were tested on Perl data set, they were tested on PA 100K 1 lakh data set, because people will always question that this is working fine on your data set. What about its performance on a public data set? That's the reason I'm showing you some results which are actually, tested on public data sets. Okay, so this is how, pedestrian attribute recognition actually works. And finally, you see when we, when we compared it with RAP and PETA, because these data sets are also extremely important, RAP and PETA. So what it shows that across all data sets, whether you talk about PAL, whether you talk about PA100, whether you talk about RAP or PETA, in all cases, you will find that the method with the clip-based architecture which has been proposed here, it is actually outperforming all these methods. This is what is the takeaway, and this is I'm not saying that people have not done better than this one, because this is 1 year old research. You can see that probably in the last 1 year a more advanced techniques came with a more complex encoder. I'm using here VIT based encoder sometimes, and in some cases we have used clip based models. But people have come up with better models also during the last 1 year. You can look into those models. I'm not going into those models, but what I'm trying to say, this domain is quite active now. And if you see that people have started working on it, right? And when we also did cross data set training, trying to understand that if you basically train with, on a particular data set, cross data set validation, like you train it on one data set, test it on another data set. So how this basically performs well. If you look into see your training data set is Perl, okay, your method is performer B or clip CP. When you tested on PETA, how the performance looks like. So you can see that you are gaining something, whenever you are using the data set, Perl data set. Similarly, when you are using the PETA data set, okay, you see that it's basically you are losing something, right? So that means PETA data set, when you train it on PETA data set, it is actually failing on Perl data set. So that means either this data set, Perl data set, which has been designed is quite challenging, or the PETA data set is not challenging enough. So it could not actually train the models properly. Similarly, you can see PA100K. PA100K was, it is highly standard data set for pedestrian attribute recognition. But if you see when it was tested on Perl or PETA, it is basically the performance is degrading. So it's 10% below. So that is where the challenge comes, right? So and it shows that if you come up with a challenging data set like Perl, okay, it is possible that some of the existing models may perform poorly as compared to their performance earlier. So that is what one point. So qualitative analysis, I can show you some results where, if you see the classification, and sometimes it is quite good for some, but if you look into the upper body, so if you see the ground truth is says that upper body color is white, it is saying 0.95 as white, so it's quite good. Hair type bald, so here also showing hair type bald 0.77. So viewpoint is back. You see that viewpoint is 0.78. It is also showing back. You see that weather is snowy, it's showing 83, 0.83 is the weather is snowy, whether the ground truth is snowy, right? Body posture is standing, you see that it's showing 0.51, it is basically sitting. Body posture is sitting, Now the point is that here it is sitting and standing. This is quite confusing. Like that's why it basically says that 0.51. 0.51 is basically 50%. So that means the classifier has no role to play here. So that means for some postures, it is really difficult even to explain that whether it is sitting posture or standing posture. Currently, if you look into it, it's basically a person is bicycling. So essentially it's a sitting posture, but the posture seems to be straight way. I mean, so that as if somebody is, standing there itself. So that's why the confusion comes here. If you look into it, this looks like a person is standing, slightly bent and standing. So that is the reason even the model gets confused. So here actually, if you see, hat is not observable, hat is not present. He is saying that with 0.35 because this image itself is quite confusing to say like this one, right? So when you see the performance of deep mark and VTB and hours on a particular on some cases where there are predictions, you see that in many cases we are performing better than VTB and obviously the deep mark, because deep mark is a benchmark which came pretty late, and it is considered to be one of the best methods of doing the pedestrian attribute recognition. Okay, and then we have also tried pedestrian attribute recognition using a hierarchical VIT-based clustering. So where multiple appearance of the same attribute in adverse weather conditions come, where a vision transformer-based approach that categorizes attributes into different spatial granularity levels and employs diverse patch formation has been used. So, so this has been again tested, and I'll show you in brief that how the approach actually works. So there were VIT architecture was adopted at 3 different levels at at a 8x8 block in L2 and 8 blocks in L2, and this is 16 blocks in L1. So basically we created patches at very fine level, then mid level, and then the high level patches, right? So some of these patches actually help to identify certain portion of the person. Some of these patches help to identify another portion, and then by combinations we found that this architecture actually plays good. So when we tested on it, we found that because there were how to implement, how do we basically decide that what is the patch size, what are the granularity levels. So after so many combinations and tested and trying, we found that maybe 16, 8 and 8 consecutive VIT blocks for L1 and L3 will work. And then you can see that the Abelson study, how it basically performs. So when we have tested with our methods, we found that on 3 data sets, including RAP, PETA, and PA 100K, this method was performing well. I mean to say that it is comparable. It's not always well. For example, we don't perform that good on PETA dataset as compared to performer, but it is reasonably close to 88.66. But whereas these two, it is performing well, right? So, and some of the qualitative results using these methods, you can see that DeepMer is still one of the method where basically it does, its accuracy is low, but how ours range is quite higher side. If you see on the these graphs actually show that we are actually outperforming all the methods when we talk about the values accuracy value. I mean to say that the confidence level is ours is always on the right side. So that means we are able to predict it on the higher side, barring a few cases. For example, this one, for some attribute, it is saying that ours is in between, whereas VIT block says that it's confidently it is female. So in some cases we are not performing well, but in majority of the cases, for example, this one where the deep mark says that it is face right, we are not so confident in saying that this is face right. So these are some of the examples which which I am showing it to you. So what are the takeaways from this entire, second part of the session is basically the pedestrian attribute recognition is important in terms of security and surveillance, right? So in modern day surveillance systems, you need to identify person with some attributes. So somebody is carrying gun, somebody is carrying a children, somebody is carrying a bag, somebody is carrying something which can be of suspicious in nature. All these things are extremely important with respect to modern surveillance. Okay. And pedestrian attribute recognition can be used for group re-identification also, person re-identification, personal retrieval, and scene understanding essentially it leads to. One challenge is data imbalance, because some attributes may be highly, dominating, some attributes may be low. Okay. But our, observation is that clip-based models can be used as a detector if one able to convert ground truths into textual description. So that means because of the VLMs, now these clip models are quite becoming quite strong, and it can actually perform very well with respect to this context. Okay. So with that, I would like to, stop my presentation, and I would like to take up questions from you if you have anything in your mind.
Yeah, participants, if you are having any queries, you can write it in the chat box. Yeah, sir, actually, there is one question. Can you tell the name of the paper? But not sure, Dr. Sweta, can you please mention?
Okay, so what I will do, I will actually paste one link where all these papers are there itself. So I think it is better if they can go through this one, they will get everything available into my website. That is better. So I'm just pasting this one into the chat box. Where is the chat box? Yeah. So I am sharing my website details, where you will go to each and every paper in details. It is there with the title, with where it has been published. So you look into the conference part and look into the journal part. You will find some papers are published in journal, some papers are published in conference. So for example, pedestrian attribute recognition, the last work which I am talking about, it is in WSCV 2025. So PARL data set, so which is basically clipping imbalances. This paper, I'm just showing it to you. This is the paper. This is the paper, WCV 2025. If you are talking about the data set of the anomaly paper, which is basically a pattern recognition paper, which I will show you this paper. Yeah, rare anomaly. It's a pattern recognition 2023 paper. So I think everything is listed there itself. If you go through, this is the second one is a journal one. But if you would like to know more about this, these papers are, you can download it. Datasets are also available, like PARL dataset we have already shared, and RARNM is already in the public domain. So we want people to use. Even the multi-perspective dataset is also online. Like, yeah, this paper I'm sharing with you, multi-perspective. This is another dataset paper, which is also, but this is a large one. We have not actually uploaded it, but you can request the author to get the dataset. Okay, so if you are interested to, work on these datasets, because essentially we create these datasets to ensure that people can use these datasets, right? So that is what our objective is.
So any other queries, participants, if you are having? So there is one query in the chat box. What can be done for the computation needs for video analysis. Okay.
Computation needs means you have to go for GPU, or either you buy GPU or you rent. I mean, you go for subscription. I know that buying GPU maybe can be costly, but even if you buy it for cloud-based services also, they are not that cheap. So it depends on what is your requirement. If your requirement is for a short period, then you can actually go for subscriptions, right? With a good internet speed, you can use it. But again, I don't find it that much economical because my work is purely on computer vision and LLM. So that's why I actually procured a few servers. Even that is becoming insufficient for my research team. I don't know. I mean, in India, we don't have that much availability of, hardware which can actually, run these large LLMs, large VLMs. They require a lot of GPUs. More than 80 GBs of, GPUs. Where do you get it? Because they're pretty expensive, right? So that is what. It's a problem, but somehow you'll have to find it out either through collaboration or through some project somewhere else. You'll have to go for it.
Okay, I think so. There are no questions. Yeah, I, on behalf of Department of Computer Science and Engineering and ICT Academy at NIT Jaipur, would like to thank you, sir.
Thank you
for accepting our request and delivering a wonderful talk on visual surveillance. So you've also discussed from these basic concepts of surveillance, right, to the advanced level, how VLMs are been integrated into such kind of systems to make it even more stronger. So thank you so much, sir, once again for sharing your valuable knowledge with us.
Thank you.